Reading Club, everybody. It's 9 o'clock on Saturday, March 4th. The 4th of March, the first Saturday of March. I did not do nearly enough writing this week. Not nearly enough writing this week for me to be able to read. See, last time I did Reading Club and I wrote around 4,000 words in a week. And I could... No, I think it was 3,000. I think it was 1,000 up on that. So I did mostly all of Reading Club with my original content, which is what I'm aiming to do right now. I am going to be changing the original Reading Club, which is just pictures of me reading, to what I call a study group. And that's a different story. You'll see study group in a little while. I'm still thinking about the way I want to do it. But that'll be back. I'm going to cue up the music here in a second, and we're going to get to reading. You can see my half-painted orcs here. We're going to be reading what is Waaagh, Teefy, Wurr, Krumpa. And in the orc language, that means he's Teefy, got a lot of money, he's flashy, he's got a lot of teeth. Wurr is fast, talks fast, and they call him Wurr because he grew fast. Oak, he's clever. Krumpa, that's just a word. But since he's a rapping orc, his name is a word play. Teefy Wurr Oak Krumpa, which is basically means like clever mouth, almost. He's got a fast, clever mouth. But I don't think the orcs quite realize that one. They just talk yeah. We're gonna cue up the music. This is Puddles of Infinity that see beneath our feet. I need to download more music to rock and foobar. I used Foobar 2000 to do this. I've used Foobar 2000 for a long time, actually. Really appreciate myself some Foobar. Some nice Foobar 2000. Come on, man. There we go. I was not putting things in the right place. So, yeah, I'm just take all those. Take that and these. And a couple more. I'll just drop those in there. I think we're on shuffle. No, we're not on shuffle, so going to do. There we go. We're on the playback random. Alright. We got the music cute. When I learned to talk, we got the music cued. We have the orcs here, as you can see. And if you watch any of my painting videos, they're coming along. There's a lot of things left to be done for them, but it's just a giant experiment for me. Now we're a whole like 8 minutes in right now. Oh, only 5, but the whole 5 minutes in. And we ain't done any reading. So we're at 9:05, 5 minutes into Reading Club. No reading. Let's do it. Let's get it. On the moon of Masperon Prime, the Bad Moon's infamous warlord Grimscraggus Squigstomper arrived to invade the planet and claim the system. Most of their fleet, crashing through pilot error or enemy fire, was annihilated. Millions of orcs swarmed the planet and the moon, to be met by the Alceritas Mortis. I have a problem saying Alceritas Mortis. It's a Alacrious death in Latin. Chapter, along with the Imperial Guard. A massive death planet of green forests, icy plateaus, of bone-arid deserts. The planet's defenders. I'm gonna make a little note. Mascaron Prime's defenders. And one of those. The planet's defenders and orcs met in a craggy, wasted desert. Another note. Didn't finish that. Grimscraggle was rightly clever. Grimscraggle was a rightly clever git and arranged a blockade from the moon's relief force. However, he loved fighting as much as any orc and got stuck into a massive apocalyptic battle against the defenders of mankind. During the clash, one of the relief ships made it into the atmosphere. Just as the defenders cheered for their salvation, an orc vessel smashed it from the skies. Both ships exploded, raining massive chunks of shrapnel on the battlefield below. Many orcs were wandering about, bewildered, fighting survivors of their imperial foes. Here and there, shattered gargants and titans, now burned out husks of their former struggle. Two knobs wandered the wastes. I've adapted a lot from my other story because I liked the way that progressed. They found a power claw whose previous owner had been completely vaporized, saved his weapons. Both knobs, seeing the larger than normal power claws, was thrown out of the smoke in some sort of secondary explosion. Both carried only a recovered chopper each. Teefy, Wurr, Krumpa, at that time called Teefy, was slightly faster, cutting off the arm of Arg and crushing his skull. I kept Arg crushers, gets hitters. I kept most of the stuff, but there's also enough for. There's a lot of. This is it's about 50-50 from the last draft to this draft. A few orcs staggered in, just a few more knobs, each seeking to make that claw their own. They waited, making faces for a long time. Making faces for what is a long time for blood-crazed orcs. During these moments, Teefy severed his arm, holding the claw with his chopper. Flinging his old weapon over his shoulder, he picked up the claw, rammed it at the stump and the stump together. For whatever reason, it worked out. The first spasms of life goring Aka, nearly severing him in half. Not intimidated, the orcs pressed their advantage of numbers. The best weapon possessed by Grasbad was possessed by Grasbad. Nope. I didn't actually do any checking on this because I didn't. Like I said, I didn't do enough writing this week, so there was no spell checking or anything. It was this is just a mess, y'all. Grasbad unleashing the best weapon was possessed by Grasbad, unleashing a gleeful amount of Daka upon the advancing war boss. One of Teefy's eye, one blew out one shell. No, I should actually put like bullet. Blew out Teefy's eye. Blew Teefy's eye out. He got within arm's reach and severed Grasbad's head, taking the twin leaf shooter for himself and menacing the rest of the knobs. Having to cut the rest of the knobs present. Having to cut off the arms of Ruck, an orc who dual-wielded choppers and was not impressed. Nope. Many boys had come staggering in the time it took for Teefy to assert his dominance. They needed no convincing not to mess with the mob of knobs. Arg attaching himself to the mob of command of the mob Arg attaching himself to command the mob for his newfound war boss. They all similarly only had choppers, but during their time milling about, mostly everybody found a slugger or shooter. While they were still milling about, lifting up a rock and throwing it, to be lifted up by another curious orc. A pain boy followed a weird boy into the camp, seeing a massive pile of teeth and Waaagh energy that could be made. Note, seeing a massive pile of teeth and presence of Waaagh energy. Yep. I just typed that one in real quick. The Bad Moons the Bad Moons offered him many of those teeth. The pain boy began to work medically and cunningly. During his reattaching of heads, a few power claws, and extra eyeballs, the weird boy was living up to his name. Drooling glowing slime and bulging out of his eyes, similarly leaking a similarly glowing substance. Bulging his eyes, leaking a similarly glowing substance. The pain boy, in a fit of rage, put down his chest of teeth before his first blow could fall, though the Waaagh energy of the weird boy vaporized them both. They had been drawn to the massive Waaagh energy. This, however, had a drawback. The one major advantage being how fast Teefy was growing. The boys calling him Teefy Wurr because of how fast he grew to war boss size. The knobs in the first scuffle, all besides Arg, became Teefy's retinue of personal body knobs. They called themselves Teefy Wurr's Gets Moves. And this also became the name adapted by the boys and the whole war band. The boys called themselves Arg's Gets Hitters! And this was their first boys knob. The entire mob, before heading out, gathered up odd armor and what missing weapons they could. They did not wander for more than 30 meters before another explosion and what was a plasma round could be seen. Charging forward headlong, some orcs were vaporized, but the fight was only between a smattering of orcs and space marines. Though there was a dreadnought, but only one, and one Terminator, seeing that only death would come for all the marines left. First the captain and sergeant First was the captain and sergeant to retreat, but the tactical squad seemed to be doing relatively nothing, but seemed to stay longer than everybody else. Right before they would surely perish, they disappeared as if in some sort of unfortunate accident. And that's actually leading into my other chapter that I'm writing about Space Marines, the Elisaritas Mortem chapter, the Lacrious Death. It's called the Lacrious Death. I'll explain it afterwards. We've got like one paragraph left. More Bad Moons joined Teefy Oak's warband. They were easily convinced. I gotta specify that it's just not Bad Moons showing up. It's the orcs that they found there were more Bad Moons. And this is a Bad Moon warband. They were easily convinced of the Waaagh to come. A squad of knobs that before the attack boasted a vast array of combi weapons. Only one held his combi scorches still. His three companions' own knobs only had choppers and shooters. Every orc and boy, every knob and boy already in odd armor. Wazbaz Burndeck was the head. So I gotta name Wazbaz's Knob Squad. And yeah, let's talk about it. So Teefy Wurr Orc's gonna be a rapper orc who's a bad moon because of the braggadocio of the bad moons. So I think it's fitting that he's going to become a war boss famous for flashiness, wearing long chains and all that, and that he's a bad moon. Here's my war boss fig. If you've seen the battle for Veridos, war boss fig, I want to get like a little tiny mic that pops down off the side of the fake eyeball and goes over his mouth, because in the story when they find this thing, they're gonna find it with like a speaker setup, and it will probably be bumping some sort of music, and or it will be bumping rap music, and the orcs will figure out like that they like rapping, or that like they'll just already know that if I've got to figure out some way to get orcs to, oh shit, they could do like really ghetto, I'm just cleaning my brush out because I'm a psycho. They could just do like really gutter, like really hood, poorly pronounced orc rap. Like, that's a great idea. They will know what rap is, but like orc rap is like, it's like Little Yachty. It's mumble rap, like it's more like singing than what they would actually be doing. And the whole idea is that they're gonna pick this thing up, they're gonna find a microphone on it, and they're gonna be like, what? And Teefy Wurr Orc's gonna be like, ois, I likes this rapping thing. And then he's gonna form a rapping orc Waaagh, where there are a bunch of rapper orcs, and they have chains and microphones and trucks that look like 6-4s and stuff, like old school like cruises and stuff from like that hood that the really hood dudes would, really hood types would drive, like really, like, you know, the long, like the old school long stretches. Yeah. Yeah. So yeah, that's it. I can read you the start of the Elisaritas Mortem chapter in 111. Elisaritas Mortem, 11th Company, 1st Platoon, A-Team, or 11th Company, 1st Battalion. I'd actually kind of want it to be Elisaritas Mortem, 1st Battalion, 11th Battalion, 11th Company, 1st Platoon. I just don't know which. Basically, the idea is that the squad of space, the squad I'm going to be writing about in 111 are, you know how in Red versus Blue, they're a bunch of failures and they like screw around the whole time, and they never really get anything done. That's what 111's gonna do. They're gonna be like rolling ones all the time. They're gonna be incredibly ineffective, and when you want them to break away, they won't. Basically, they'll be the worst. That's the whole idea behind 111. They're like failures. They're like failures of Space Marines that are kind of just running around like, but you know, they're still Space Marines. I'll mask on Primus moon, because these guys are on the moon. No, actually I gotta change that because they're on Maspron Primus. On Maspron Primus, a great orc woe had been broken. The Elisaritas Mortem chapter of Space Marines, non-codex chapter, spending most of all their times warring in the ghoul stars. I'm actually gonna change that, and they're gonna be warring in the Halo stars, because they don't exist inside of the Imperium. They're like in one of those planets that was abandoned outside the Imperium, breaking not only the back of a foul orc war boss, but almost annihilating every brother from the 1st, 2nd, 6th, 10th, and 11th companies. That's as far as I got. Because then I was like, had to go write other stuff. It's like, hey, click, and decided that I should write the Elisaritas Mortem chapter. And this has a whole 2 sentences in it. Elisaritas Mortem. Many chapters, mysteries remain unknown in the grim dark future. Unacknowledged by the sons of Guilliman on a planet in the halo stars abandoned by the Imperium's light. That's where the Elisaritas Mortem chapter hails from. The Alacrious Death, and I named them Alacrious Death to counterpoint, because like the rest of the the Alacrious Death chapter is like really high end, like super tough with a tough guy's Space Marine chapter. But 111's like their kind of flunky department. So while 111 is running around basically failing at everything, the Alacrious Death chapter is going to be all a bunch of like serious tryhards that'll be like, "What are you doing?" That's the idea. While these guys are like, they're the comedy gag characters to a very not comedy gag chapter, but I'm playing it so serious in that chapter because of the way I'm going to be making these guys a story, the 111 story, because I think that playing them is like, they're basically all Rogel Dorn. They're like, yeah, they're basically all, I don't know, they're all unbending, unwavering, just knob eaters, basically. Yeah, knob eaters. But yeah, that's where I'm going with the Elisaritas Mortem and 111. It ties into the Teefy Ulk. All of the appearances by Elisaritas Mortem until I get into like actual battles with them are going to just be 111 running away. He'd be like, "Nope, we're leaving." Yeah, and that's how they're gonna do for a while. And then when I get into actual battles, when I get these all painted, I get them into battles, we'll continue writing in a different method. Alright. 23 minutes in. Let's go over and check out those Feynman physics lectures I promised. This is going to be a heavy going. You guys like that as much as I did? I ate pizza and a bunch of spicy food yesterday, and I woke up feeling great. So good when I woke up this morning. Don't eat tons of pizza and tons of spicy food in the same day. You just feel like garbage when you wake up. I think you already know that. Boop doop doop. Alright. I don't think I've read a lot of this. By a lot of this, I've read like part of the first lecture, but we will continue on. I'm at 1.3. The atomic process, 1 part 3 under the first lecture. I was doing this for a podcast and I stopped. Like I started again, I stopped. So much for the descriptions of solids. Right underneath figure 1.5, like when you see the water evaporating into air figure, directly below that is where you will join us. So much for the descriptions of solids, liquids, and gases from the atomic point of view. I will post this in chat so you guys can read it with me. Or just read it for yourselves. I should actually be reading chat, which I'm not doing. Well, can't really do that when I'm reading, so. There's that. That's a thing. Boop doop doo. Hey, I got a new spam. I got some more spam, guys. Alright. Posting them. I don't have 2 monitors up right now. That's why I can't read chat and my documents at the same time. I could shrink the windows down, but that would interfere with my already labored reading process. So, you guys want to read that with me? Feel free. Because we're going to start out at figure 1-5 underneath lecture 1, part 3, atomic processes. So much for the description of solids, liquids, and gases from the atomic point of view. However, the atomic hypothesis also describes processes, and so what we shall look at now, a number of processes from an atomic standpoint. The first process that we shall look at is associated with the surface of water. Oh, I'm going to blow this up so it stood up. What happens at the surface of the water? We shall now make the picture more complicated and more realistic by imagining that the surface is in air. Figure 1-5 shows the surface of water in air. We see the water molecules as before forming a body of liquid water, but now we also see the surface of the water. Above the surface we find a number of things. First of all, there are water molecules as in a stream. This is water vapor, which is always found above liquid water. There's an equilibrium between steam vapor and water, which will be described later. In addition, we will find some other molecules. Here, 2 oxygen atoms stuck together by themselves, forming an oxygen molecule. There are 2 nitrogen atoms also stuck together to make a nitrogen molecule. Air consists almost entirely of nitrogen. Nitrogen, oxygen, some water vapor, and lesser amounts of carbon dioxide, argon, and other things. So, above the water surface is air, a gas containing some water vapor. Now, what is happening in this picture? The molecules in the water is always jiggling around. From time to time, on the surface happens to be hit a little bit harder than usual, and it gets knocked away. One on the surface happens to get knocked away. Alright. It is hard to see that happening in the picture because it is a still picture. But we can imagine one molecule near the surface has just been hit and is flying out. Or perhaps another one has been hit and is flying out. Thus, molecule by molecule, the water disappears and evaporates. But if we close the vessel above, like I do with my wet palette, if we close the vessel above, after a while we shall find a large number of molecules of water amongst the air molecules. From time to time, one of these vapor molecules comes flying down to the water and gets stuck again. So we see that it looks like a dead, uninteresting thing, a glass of water with a cover, that has been sitting there for perhaps 20 years. Really contains a dynamic, interesting phenomenon, which is going on all the time. To our crude eyes, nothing is happening. But if we could see a billion times magnified, we could see that from its own point of view, it is always changing. Molecules are leaving the surface, molecules are coming back. Why do we see no change? Because just as many molecules are leaving as are coming back. In the long run, nothing happens. But if we take the top off and blow the moist air away, replacing it with dry air, then the number of molecules leaving is just the same as it was before. because this depends on the jiggling of the water. But the number coming back is greatly reduced because there are so many fewer water molecules above the water. Therefore, there are more going out than coming in, and the water evaporates. Hence, if you wish to evaporate water, turn on the fan. Here is something else. Which molecules leave? When a molecule leaves, is it due to an accidental extra accumulation of a little bit more than ordinary energy, which it needs if it is to break away from the attractions of its neighbors? Therefore, since those that leave have more energy than average, the ones that are left have less average motion than they had before. So the liquid gradually cools if it evaporates. Of course, when the molecule of vapor comes from the air to the water or below, there is a sudden great attraction as the molecule approaches the surface. This speeds up the incoming molecule and results in a generation of heat, so that when they leave and take away heat, when they come back, they generate heat. Of course, when there is no net evaporation, the result is nothing. The water is not changing temperature, but if we blow on the water so as to maintain continuous preponderance of the number of if we blow on water so as to maintain a continuous preponderance in the number evaporating, then water is cooled. Hence, blow on soup to cool it. Of course, you should realize that the processes just described are more complicated than we have indicated. Not only does the water go into the air, but also from time to time, one of the oxygen or nitrogen molecules will come and get lost in the mass of water molecules and work its way into the water. Thus, the air dissolves the water. Oxygen and nitrogen molecules will work their way into the water, and the water will contain air. If we suddenly take the air away from the vessel, the air molecules will leave more rapidly than they come in, and in doing so will make bubbles. This is very bad for divers, as you may know. And then we come into figures 1.6 and 1.7. It is salt dissolving in water, and there's pictures of like chlorine and sodium. And then there's figure 1.7, which is some sort of graph rock salt. Not exactly Alright. Now we'll figure that out. We'll figure that out in a second. Now if we go on, hold on, I gotta make sure I'm not in Discord. Now if we go on to another process, in figure 1.6 we see it from an atomic point of view, a solid dissolving in water. If we put a crystal of salt in the water, what will happen? Salt is a solid, a crystal, an organized arrangement of salt atoms. Figure 1.7 is an illustration of a three-dimensional structure of common salt, sodium chloride. Strictly speaking, the crystal is not made from atoms, but what we call ions. An ion is an atom which either has a few extra electrons or has lost a few electrons. In a salt crystal, we find chlorine ions. Chlorine atoms with an extra electron. Sodium ions, sodium atoms with one electron missing. The ions all stick together by electrical attraction in the solid salt. They're trading ions, huh? Electrons, not ions. But when we put them in the water, we find, because of the attractions of the negative oxygen and positive hydrogen for the ions, that some of the ions jiggle loose. In figure 1.6, we see a chlorine ion getting loose, and other atoms floating in the water in the form of ions. I'm just stupid. This picture was made with some care. Notice the example that the hydrogen ends of a water molecule are more likely to be near the chlorine ion, while near the sodium ion, are more likely to find the oxygen end, because the sodium is positive and the oxygen of the water is negative. They attract electrically. I'm going to go up and look at that. Okay. Oh. Too dumb. Can we tell from this picture whether salt is dissolving in water or crystallizing out of water? Of course we cannot tell, because while some of the atoms are leaving the crystal, other atoms are rejoining it. The process is a dynamic one. Just as in the case of evaporation, it depends on whether there's more or less salt in the water than the amount needed for equilibrium. By equilibrium we mean the situation in which the rate at which atoms are leaving just matches the rate in which they're coming back. If there is almost no salt in the water, more atoms leave than return, and the salt dissolves. If there's too many salt atoms, more return than leave, and the salt is crystallizing. In passing, we mentioned the concept that a molecule of a substance is only approximate and exists only for a certain class of substances. It is clear that in the case of water that the three atoms are actually stuck together. It is not so clear that in the case of sodium chloride in the solid. It's not so clear in the case of sodium chloride in the solid. There is just an arrangement of sodium and chlorine ions in a cubic pattern. There's no natural way to group them as molecules of salt. What? Hey? Reading this stuff makes you feel real stupid, bro. I got you, Mac. I'm picking up where you're laying down. Damn, this is kind of trippy though. So it's like, we'll read that first one again. In passing, we mentioned the concept of a molecule of a substance is only approximate and only exists for a certain class of substances. It is clear that in the case of water, three atoms are actually stuck together. It is not so clear that in the case of sodium chloride in a solid, there's just an arrangement of sodium chloride in cubic patterns. There is no natural way to, yeah. Isn't that crazy? There's no salt stuff. Salt's free form, bro. Salt's like improvising, man. Salt's like out there, bro. At least in its molecular structure. Well, we'll skip the paragraph there. Returning to our discussion of solution and precipitation, if we increase the temperature of the salt solution, then the rate at which atoms are taken away is increased. And so it is the rate at which atoms are brought back. It turns out to be very difficult in general to predict which way it is going, whether more or less of the solid will dissolve. Most substances will dissolve more, but some substances will dissolve less as the temperature increases. In all of the processes which have been described so far, the atoms and ions have not changed partners. But, of course, there are circumstances in which atoms do change combinations, forming new molecules. This is illustrated in figure 1.8. A process in which the rearrangement of atomic partners occurs is alright. This is illustrated in figure 1.8. A process in which the rearrangement of the atomic partners occurs is what we call chemical reaction. Okay. That made a whole lot more sense when I didn't skip 3 words. The other process so far described are called physical processes, but there's no sharp distinction between the two. Nature does not care what we call it, she just keeps doing it. Neil deGrasse Tyson said it this way: the universe doesn't have to make sense to you, is what he said. It's under no responsibility to make any sense to you. Or me. This figure is supposed to represent carbon burning and oxygen. In the case of oxygen, two oxygen atoms stick together very strongly. Why do not 3 or even 4 stick together? That is one of the very peculiar characteristics of such an atomic process. Atoms are very special. They like certain particular patterns, certain particular directions, and so on. It is the job of physics to analyze why each one wants what it wants. At any rate, two oxygen atoms form a saturated and happy molecule. Figure 1a. Carbon burning and oxygen. The carbon atoms are supposed to be in a solid crystal. Getting some water. Now, for example, one of the oxygen molecules can come over to the carbon, and each atom can pick up. Let's start that over. Carbon atoms are supposed to be in a solid crystal, which could be graphite or diamond. You can apparently you can. Side note: you can burn a diamond in the air. Now, for example, one of the oxygen molecules can come over to the carbon, and each atom can pick up a carbon atom and go flying off in a new combination, carbon-oxygen, which is a molecule of the gas called carbon monoxide. It is given the chemical name CO. It's very simple. The letters CO are practically the picture of the molecule, but carbon attracts oxygen much more than oxygen attracts oxygen, or carbon attracts carbon. Therefore, in this process, the oxygen may arrive with only a little energy, but the oxygen and carbon will snap together with a tremendous vengeance and commotion. Man, yeah, that must be some sort of insanity, because they kind of, if they were traveling off of momentum into each other, this is a really poor way to put it. Say each atom was a car that was coasting, right? And they're running out, but as soon as they get close together enough, they got like magnets on the front of each other, and they start running off their own momentum, and BAM! Well, what he says is they will snap together with a tremendous vengeance and commotion, and everything near them will pick up the energy. A large amount of motion energy, kinetic energy, is thus generated. This is, of course, burning. We are getting heat from the combination of oxygen and carbon. The heat is ordinarily in the form of the molecular motion of the hot gas, but in certain circumstances, it can also be so enormous that it generates light. This is how one gets flames. In addition, the carbon monoxide is not quite satisfied. It is possible for it to attach another oxygen, so that we might have a much more complicated reaction when the oxygen is combining with the carbon. While at the same time, there happens to be a collision with a carbon monoxide molecule. The oxygen atom could attach itself to the carbon monoxide and ultimately form a molecule composed of one carbon and two oxygens, which is designated as carbon dioxide. Super famous. At least everybody be talking about that, carbon emissions and whatnot. If we burn the carbon with very little oxygen in a very rapid reaction, for example, automobile engines, where the explosion is so fast that there's not time for it to make carbon dioxide, a considerable amount of carbon monoxide is formed. In many such rearrangements, a very large amount of energy is released, forming explosions, flames, etc. Yeah, a lot of carbons will just kind of control detonations. Depending on the reactions, chemists have studied these arrangements of the atoms and found that every substance is some type of arrangement of atoms. To illustrate this idea, let us consider another example. If we go into a field of small violets, we know what the smell is. It is some kind of molecule arrangement of atoms that has worked its way into our noses. First of all, how did it work its way in there? That is rather easy. If the smell of some kind of molecule, if the smell is some kind of molecule in the air jiggling around, being knocked every which way, it might accidentally have worked its way into the nose. Certainly it has no particular desire to get up into our nose. It is merely one helpless part of a jostling crowd of molecules, and in its aimless wanderings in this particular chunk of matter, it happens to find itself in the nose. Figure 1.9. Odor of violets. Now, chemists can take special molecules like the odor of violets and analyze them. Tell us the exact arrangement of the atoms in space. We know that the carbon dioxide molecule is straight and symmetrical. OCO, that can be determined easily, by physical methods. However, even for the vastly more complicated arrangements of atoms that Figure 1.9 is that are in chemistry. However, even more vastly complicated arrangements of atoms that are in chemistry, one can, by a long, remarkable process of detective work, find the arrangements of atoms. Figure 1.9 is a picture of the air in the neighborhood of a violet. Again, we find nitrogen and oxygen in the air, and water vapor. Why is there water vapor? Because the violet is wet. All plants transpire. However, we see a monster composed of carbon atoms, hydrogen atoms, which have picked up a certain particular pattern which to be arranged. It is much more complicated arrangement than that of carbon dioxide. In fact, it is an enormously complicated arrangement. Unfortunately, we cannot picture all that is really known about it chemically, because the precise arrangements of all the atoms is actually known in 3 dimensions, while our picture is only in 2 dimensions. The 6 carbons which form a ring do not form a flat ring, but kind of a puckered ring. Okay. I lost my place. Oh no. All the angles and distances are known, so a chemical formula is merely a picture of such a molecule. When the chemist writes such a thing on a blackboard, he is trying to draw, roughly speaking, in 2 dimensions. For example, when we see a ring of 6 carbons in a chain of carbons hanging in the end with an oxygen For example, when we see a ring of 6 carbons and a chain of carbons hanging on the end with an oxygen second from the end, 3 hydrogens tied to that carbon, 2 carbons and 3 hydrogens sticking up here, etc. Yep. I will just finish it up. We're almost there, guys. How does the chemist find what the arrangement is? He mixes bottles full of stuff together, and if it turns red, it tells him that it consists of 1 hydrogen and 2 carbons tied on here. If it turns blue, on the other hand, that is not the way it is at all. This is one of the most fantastic pieces of detective work that has ever been done. Organic chemistry to discover the arrangement of atoms in these enormously complicated arrays. The chemist looks at what happened when he mixes two different substances together. The physicist could never quite believe that the chemist knew what he was talking about when he described the arrangement of atoms. For about 20 years, if it had been possible in some cases to look at such molecules, not as quite as complicated as this one, but some which contain parts of it. Alright, let's run that one back. The physicist could never quite believe that the chemist knew what he was talking about when he described the arrangement of atoms. For about 20 years, it had been possible in some cases to look at such molecules, not quite complicated as this one, but some which contain parts of it. By a physical method, it had been possible to locate every atom, not by looking at colors, but by measuring where they are. Lo and behold, chemists were almost always correct. Turns out that in fact the odor of violets are three slightly different molecules which differ on the arrangement of the hydrogen atoms. Only in the arrangement of hydrogen atoms. One of the problems of chemistry is to name a substance, so that we will know what it is. Find a name for this shape. Not only must there be a name to tell the shape, but it also must tell if there's an oxygen atom, there's a hydrogen atom, exactly what and where each atom is, so we can appreciate the chemical names. The chemical names must be complex in order to complete. You see the name of this thing in the more complete form that will tell you the structure of its. Okay, 4, 2, 3, 4, or 2, or 3, or 6 tetramethyl 5 cyclohexanyl 3 butane 2,1, and that tells you that this is the arrangement. We can appreciate the difficulties that chemists have and also appreciate the reason for such long names. It is not that they wish to obscure, but that they have an extremely difficult problem in describing molecules and words. How do we know that there are atoms? By one trick mentioned earlier, we take a hypothesis that there are atoms, and one after the other results come out of the way we predict, as they ought to if things are made of atoms. There is also somewhat of a more direct evidence, a good example of which there is the following. The atoms are so small that you cannot see them with a light microscope. In fact, not even with an electron microscope. With a light microscope, you can only see things which are much bigger. Now, if the atoms are always in motion, say in water, and we put a big ball of something in the water, a ball much bigger than the atoms, the ball will jiggle around, and much as in a push ball game. Whereas a great big ball is pushed around by a lot of people, the people are pushing various directions. The ball moves around the field in a regular fashion, so that in the same way the large ball will move because of the inequalities of the collisions on one side to the other, from one moment to the next. Therefore, if we look at very tiny particles, colloids, in the water through an excellent microscope, we are seeing perpetual jiggling of the particles, which is the result of the bombardment of the atoms. We call this Brownian motion. We can see further evidence for atoms in the structure of crystals. In many cases, the structures deduced by X-ray analysis agree with their spatial shapes with the forms actually exhibited Bicrystals, as they occur in nature, the angles between the various faces of a crystal agree within seconds of arc, with angles deduced on the assumption that a crystal is made of many layers of atoms. Everything is made of atoms. That is the key hypothesis, the most important hypothesis in all of biology. For example, that everything that animals do, atoms do. In other words, there is nothing living there is nothing living things do that cannot be understood from the point of view that they are atoms acting according to the laws of physics. This was not known from the beginning. It took experimenting and theorizing to suggest the hypothesis, but now it is accepted, and it is the most useful theory for producing new ideas in the field of biology. If a piece of steel or salt consists of atoms, one next to the other, if a piece of steel or salt consisting of atoms one next to each other can have such interesting properties, if water, which is nothing but these little blobs, mile upon mile of the same thing over the earth, can form waves and foam and make rushing noises in strange patterns, and as it runs over cement, okay, we're gonna run that back again. Okay. If this is, it's talking about water. I was like, what? If all of this, all of the stream of water can be nothing but a pile of atoms, how much is more possible? Instead of arranging atoms in some definite pattern again and again repeated on and on, or even forming little lumps of complexity like the odor of violets, we make an arrangement which is always different from place to place, with different kinds of atoms arranged in many ways, continually changing, not repeating. How much more marvelously is it possible that this thing might behave? Is it possible that that thing walking back and forth in front of you, talking to you, is a great glob of these atoms in a very complex arrangement, such that in the sheer complexity of it staggers the imagination as to what it can do? When we say we are a pile of atoms, we do not mean we are merely a pile of atoms, because a pile of atoms which is not repeated from one to the other might as well have the possibilities. Because a pile of atoms which is not repeated from one to the other might as well have the possibilities which you see before you in the mirror. Let's run that one back again. When we say we are a pile of atoms, we do not mean we are merely a pile of atoms. Because a pile of atoms which is not repeated from one to the other might well have the possibilities which you see in front of before you in the mirror. Alright. It's 9:58. We're just going to talk for a bit. That was a lot of reading. Heavy business. That was heavy business, y'all. That's why I started screwing up at the end, because my brain started lighting on fire. Heavy stuff. We'll move on to the next one. I'm actually glad to get that out. Next time we have to supplement with Feynman physics lectures, we'll be moving on to chapter 2. Alright. Okay. So, what are we going to talk about for these 5 minutes? I think it's nuts, a few things I said there, that atoms, that there's a number of atoms that don't have he said structures like salt, salt's out there, bro. And I also like how what he stated at the end about the limitless possibilities of atoms in transference, not only of the atoms in transference, but of ourselves as piles of atoms as a force unto ourselves, we can do incredible things. You can do incredible things. For yourself, for other people, for science, man. You do all sorts of incredible stuff. You just gotta be willing to put in the work. It's a lot of hard work to get places these days, man. It's a lot of... Some people say ain't nothing new under the sun. Just, it ain't what you're doing, but how it's been done. I don't quite agree with that. But what they're driving at is people have been doing stuff for a long time. And to do it, you gotta be doing it good. So, yeah. I completely agree. There's a whole lot out there. I'm browsing my phone right now. By that, I'm going to the Warhammer 40k wiki. And, yeah. I hope you guys enjoyed that episode of Reading Club. I'll try to get more writing done next week, but if we don't, we can go back to the Feynman physics lectures again, and I'll hurt my head some more. It's 10:01. I don't want to keep you too long on your Saturday because you've got things to go do, people to see, jump around, have fun. Remember, man, if you seek hate, you're going to find hate. If you seek love, you're going to find love. I'm going to catch y'all on the flip.